So we have two chapters in my current textbook that I use that are a little bit different from the other chapters. There's not a lot of computation or specific formulas or anything in them. They're more about how to conduct good sampling in this chapter and how to do good experiments and how to do bad sampling and bad experiments so that you know how to avoid those or look out for those as well. So very, very text heavy. You could probably just read through these PowerPoints on your own, but I thought I would still go ahead and make the video summaries where I can add a little bit to it. So this chapter we're going to talk about sampling, okay? And so the idea is that you have a population, which is the entire collection of individuals that we wish to study. So for instance, this could be the entire population of the United States of America, okay? And that's way too large for us to go out and get information. I mean, they try to do what they call the census, which is when you actually collect data on the entire population. They try to do that every 10 years. But in general, something like the entire U.S. population, that's way too big to collect the data from everybody. So what we do is we take a sample, a smaller subset of the population, and collect data from them. And we want to do it using randomness in a certain way so that we're able to infer from the sample to the population. The particular numbers that we work with, and the letters kind of help you remember this, statistics are for samples, parameters are for populations. So for instance, you have your population mean, the average of whatever you're looking at, the average income of every adult in the United States versus the average income of every adult in a sample that we take would be a statistic. So that's what statistics are. They're data collected from samples. Okay? And, well, as I'll say at the bottom of the slide here, inferential statistics is all about that, how to take a smaller sample and make an inference about the parameter, how to use statistics to make predictions using probability about the parameters. So just definition here, example 1. Your local newspaper contains a large number of advertisements for unfurnished one-bedroom apartments. You choose 10 at random and calculate their mean monthly rent is $540 and the standard deviation of their rents is $80. Is each of the boldface numbers a parameter or a statistic, the $540 or the $80? Is that a parameter or a statistic? What is the population? What is the sample? Okay. So you choose 10 at random, and I would say that's going to be your sample. The ones you actually collect data from is your sample. So the 10 apartments that you randomly collect the data on. Their mean monthly rent is $540. That's a statistic because it's taken from those 10. And the standard deviation is taken from those 10. So both of those numbers are statistics. Okay. The population, this one I always say, the population sometimes could be a little open-ended into how big you assume it is. Like you might say it's all of the apartments in the entire newspaper. It says it has a large number of advertisements, so that could be the large population, and you're just doing 10 of those. Or your population could be all the unfurnished apartments in the whole city, if you're talking about like New York or Atlanta or somewhere. So a little open-ended on that. This one, I guess I would say probably the way this one's worded, I'd be going for that the sample is this large number of advertisements for unfurnished one-bedroom apartments, and then the 10 that you select is the random sample. Okay? And the numbers we have there come from the sample, so those are statistics. Okay? 540 and 80 are statistics. So the population's all unfurnished one-bedroom apartments, either completely open-ended or in that city or in that newspaper. And then the sample is the 10 randomly selected apartments. Okay, so if you're going to do this, I mean, the natural thing is to ask, how could you possibly take a small sample and use that information to infer something about a whole population when you're leaving out lots of people? Well, the important thing is your sample needs to be representative, okay? It needs to have the characteristics that the population has, okay? And we'll talk about how random sampling is the best way to try to achieve that. A lot of what we'll talk about in this section is what to avoid, some things that are very common, but why they should be avoided when they can. Sometimes it's just, well, like a convenient sample. It's convenient. It's what you can do. But the design of a sample is biased if it systematically favors certain outcomes. Okay? So if it's not a characteristic sample and it systematically favors certain outcomes, we'd say it's biased. A couple of extremely common types of samples that you run into that are biased in general, they tend to be biased, are convenient samples and voluntary response samples. Okay? So a convenience sample is you just take your sample to be the people that are easiest to get, or whatever you're looking at, whatever the individuals are, you take the ones that are easiest to get. The examples you always see are you stand outside of a building or you stand in a shopping mall and you just grab people as they come by and say, will you take my survey, or whatever data you're trying to collect. Voluntary response is when you put out the ad and people decide whether or not they want to participate. That is often, and you see those like radio call-in polls, or now they do them through Facebook or Twitter or something. Respond to our Twitter poll. Do you think Donald Trump is doing a good job as president, or something like that? Those are usually biased because it's the people that have the strong opinions one way or the other that are gonna call in or take the online poll when you do voluntary response. What you want to do when you can, and sometimes you can't in real life, but what you'd like to do is random sampling. Some sort of random sampling where everyone in the population has the same chance of being selected. That way, whatever lurking variables you have, they're going to be spread out evenly among the sample. Okay. So random sampling, you use chance to select your sample, and it's the central principle behind all the statistical sampling that we're going to talk about. Behind all of inferential statistics, we're going to assume we have random samples. The simple random sample is just where you select a certain sample size and you say, I'm going to collect this many people, and you do it in some way. Like if it's a small sample, like a class or something, you could draw names out of a hat or something, and there's lots of ways to generate random samples. There's tables of random digits, as it says here. Computers can generate what are actually usually technically called quasi-random samples because they're still using some sort of fixed algorithm, but they're giving you random digits. But in a simple random sample, every individual in the population has the same chance of being selected. Okay. For example, let's see, I can show you example 2 here. This doesn't make a good test question, I'll just say, because I have no way of knowing if you did it correctly or whether you just kind of went through and picked out 5 names, but use a random number generator to select 5 students at random from the following list. So if you were going to do that, you would want to number them. Let's see. Yeah, I talked about how to do that on the calculator here. Okay, so your calculator can generate random integers in a given range. Okay, so I can select 5 random numbers from 1 to 15. So if you hit the math button and then you use the arrow, so the math button, the third one down, and then arrow over to the right till you get all the way over to the PRB, which is probability to that column. And there's several things that say rand for random, and number 5 is the one you want, which is a random integer. Okay, you select that, and then depending on your calculator, you might get a menu or you might just have to type it, but you have your minimum value, your maximum value, and the number of numbers that you want. Okay, so in this case, I want numbers between 1 and 15, and it includes your endpoints. If I do 1 to 15, it'll pick random numbers between 1 and 15, and it could pick 1 or 15. And if you add the third number, it'll pick that many of them. I think it's possible you get repeats in that, and we say if you get repeats when you're doing random sampling, you just go until you have, say, 5 different ones. So I did that on my calculator, and I got 5 different ones. I got 15, so that'd be Hillary. 14 would be Sarah. 3 would be Irma. Number 8 would be Kathy, and number 7 would be Robert. Okay. So you have a random integer generator on your calculator that you can use. Excel and lots of other programs have ways to generate random samples from finite sets of numbers, to generate random integers from sets of numbers. Okay, so there's my sample: Hillary, Sarah, Irma, Kathy, and Robert. Okay, some other types of random sampling, or sampling that involves randomization. So to select a stratified random sampling, first classify the population into groups of similar individuals called strata. So there, for example, we could take the 50 states. Okay, so we have these groups of the 50 states, and then we randomly select 25 people from each state. That would be stratified sampling. Or we take freshmen, sophomore, juniors, and seniors at the college, and we randomly sample 100 people from each of the groups. Okay, so you divide your population first into groups based on some characteristic, and they call the groups strata with the Latin word there. And then you randomly select certain number from each of those. That's called stratified random sampling. And I will add there, depending on the characteristics of the population, you don't have to select the same number from each group necessarily. Like if you have a population that's 60% male and 40% female, you may want that to be reflected in your sample as well. Okay? Cluster sampling is kind of the opposite. You divide into groups and then you take entire groups. So like maybe we take the 50 U.S. states and randomly pick 5 of those and then go and select every one of something. I probably wouldn't take every single person in the state. Maybe you're looking at public universities and we randomly pick 10 states and then take every public university in the state and look at tuition or something. Okay, and then another one that's commonly used is systematic sampling, where if you can get an entire list of the population and get it numbered, you pick a starting point and then you take, say, every 50th person, every 100th person, every nth person. Okay? So those are some different types of sampling. Let's go ahead and do this example here, try to match up what type of sampling is being done. So these are all similar, trying to get similar information but doing it in different ways. So a study's done to determine the average tuition at San Jose State undergraduate students pay per semester. Each student in the following samples is asked how much tuition he or she paid for the fall semester. What's the type of sampling in each case? Okay. So part A, a sample of 100 undergraduate San Jose State students is taken by organizing the students' names by classification, freshman, sophomore, junior, or senior, and then selecting 25 students from each. Okay, so I just mentioned that as an example on the last slide. That's the stratified random sampling. You're dividing it into 4 groups and randomly selecting from each of the groups. That's stratified random sampling. Okay, part B, a random number generator is used to select a student from the alphabetical listing of all undergraduate students in the fall semester. Starting with that student, every 50th student is chosen until 75 students are included in the sample. Okay, that's the one we called systematic sampling, or systematic random sampling, or systematic sampling. Part C, a completely random method is used to select 75 students. Each undergraduate student in the fall semester has the same probability of being chosen at any stage in the sampling process. That's simple random sampling. Everybody has the same chance of getting picked. You have a certain number you're going to pick. That's simple random sampling. Okay, a couple more. The freshman, sophomore, junior, and senior years are numbered 1, 2, 3, and 4 respectively. A random number generator is used to pick 2 of those years. All students in those 2 years are in the sample. So that is cluster. You see, that's the opposite. If you look back at part A at the stratified, this one's your cluster, and you can see the difference between the two. And then finally, an administrative assistant is asked to stand in front of the library one Wednesday and to ask the first 100 undergraduate students he encounters what they paid for tuition for the fall semester. Those 100 students are the sample. Okay, that one was the convenience sample, where you just take the convenient sample as they walk by. And remember, that's the one that is pretty likely to be biased, because you're getting certain types of people potentially if you're just standing outside the library. One example they like, suppose you stood outside the library and instead of asking about tuition, you ask, should we charge an extra $20 a semester to buy more books for the library, or to buy new computers for the library, or something like that? The people that use the library are more likely to say yes than the people that don't. So if you stood outside the library, or if you stood outside of the athletic facility and asked a similar type of question, you might get a biased sample. So convenience sampling can very often be biased. And then just, again, you could kind of read through this on your own, but when studying, we must encounter both sampling errors and non-sampling errors. Sampling errors arise from the sampling process, such as not taking large enough samples. Non-sampling errors could be actual errors related, as it says, defective counting devices, things like that, that are not due to the sampling process, but are other types of errors. There's always some error due to sampling. If you don't take the entire population, you're never going to have the exact information about the population, so you get some sort of error. But in general, the larger the sample, the smaller the sampling error would be. Sampling bias is created when the sample is collected from a population, and some members of the population are not as likely to be chosen as others. Okay, so like the convenience sample or voluntary response leads to sampling bias. Let's see, a couple more slides here. It's important to understand sample variability, that every time you take a sample, you're going to get different answers or different information. We're going to talk about, by probability in certain situations, how we can predict those types of things. When we study inferential statistics, sample size is going to be really important. Larger samples are generally better, but even large samples can be biased if you use poor methods such as voluntary response or convenience samples. Things to look for when evaluating statistical studies. So if you're reading some report that somebody found some sort of research result, you should look and see, do they have problems with their samples? Are they self-selected samples? Okay. Are there sample size issues? Are they too small? Is there undue influence? Is a drug-making company telling you something about how wonderful their drug is? Non-response or refusal of subjects to participate. That's something that sometimes can't be avoided. You can't force people to participate in your study sometimes. So if you get people that don't participate when they were chosen, it messes up the randomness of your sample. Always be cautious with causality claims. We talked about how correlation does not imply causation. Okay? Self-funded or self-interest studies. I mentioned a drug company trying to tell you how good and wonderful their drug was. If it's self-funded, self-interested, they have a reason to try to make it look a certain way. So you got to look out for that. Misleading use of data and confounding. Remember confounding when you have lurking variables, those types of things.